All right. So we are live. We have a lot of people. And thank you so much. And sorry for the slight difficulties. I see people from Toronto, from Mars.
Hooray!
Wow, never heard this. Can you tell us where you're joining from? Not the platform, but the place. I see India. I see people from all over the place. Lebanon, nice. Hello, Jay. Have finds in Lebanon. Love it. Um, Excellent. So bam, thank you all for joining us. Happy to be here with my friend Josh and my friend Jay. And we have a lot of questions from the crowd to answer, but we will also take questions on the fly, like online. Of course, we have time to prepare the ones that I've sent earlier, so those are better. But before we do anything, a lot of big announcements. First of all, there's this wonderful book that just came out from Jay Alammar called Hands-on Large Language Models with Jay and Martin Grotendorst. Hope I pronounced it well. Why don't you say some words, Jay?
Yes. So this has been it's an exciting time. We released this book just about a month ago. We've been working on it for a good year and a half. It's a high level overview of transformers that is meant to be accessible to maybe most Python developers. It's highly visual, so it has 300 original visuals, figures that explain the various concepts that newcomers will sort of need to understand to be able to work with transformers. So it's in three parts. The first one is just touches on the architecture itself, but then the vast majority of the book is on applications. So things like clustering, classification, prompt engineering, RAG and semantic search, multimodality, and then the last part is a little bit more advanced. It's for people who need to fine tune the models. So how to fine tune representation and embedding models, but also how to fine tune and think about RLHF, DPO, preference and instruction tuning or supervised fine tuning of these models. That is part 3 of the book. We're excited to share it with people and would love feedback and would love to see what people think about it.
Amazing. And I've
Can I
had the
give you
chance
some
to look at it. It's
feedback?
amazing. Yeah, go for it.
It's like my favorite book of like the year, 2024. If I had an award for the best book, this is it. Hands-on large language models. I cannot endorse it enough and say how awesome it is.
Yeah.
I mean, yeah, I just love it. The practical applications are in fact practical. They're the kind of things that I would actually want to do, and actually kind of in some ways kind of was life-changing for me because it gave me an appreciation for encoder only transformers, like embeddings, and sort of like I understood what embeddings were, but when I read the book, I was like, it was like my head was like, oh, now I know what they're for and how they can be used in applications in a way that's really been transformative. I feel like because of this book, I learned that encoder only transformers like BERT and things like that are kind of the unsung hero of this whole AI revolution that we have right now. Everybody talks about Gen AI all the time, and they talk about ChatGPT, and they talk about anything that can generate text or images, and they're like, "This is it." And that's like, I feel like that's all cool stuff, but the real meat of stuff that's actually going to get done is going to get done with these encoder only transformers. And I learned that from this book when I read through all the applications, like, oh, this is actually useful. I'm not just like playing around or doing something with a toy. This is like something I could use for real work that I don't actually have a good alternative solution for already. So in that respect, when I read this book, it was sort of transformative of just my whole perspective of like what this AI revolution is all about, and a better appreciation of it. So I mean, if you're going to get one book this year or in the next month or in the next I won't say 6 months because I have a book coming out pretty soon. But if you're going to get one book in the next month and a half, get this one. If you're going to get 2 books in the next 6 months, get this one plus mine. So I just love this book.
Yeah. If you're gonna get 4 books, get 2 copies of Jay's and 2 copies of Josh's.
Yes.
Yeah, which we'll talk about soon.
Okay.
Yes, no, I agree. I agree. It's a wonderful book. It's got so much stuff. In particular, like there's a section on tokenization. I never knew there was a lot to tokenization, and now I know there's a lot.
Yes.
to tokenization and those kind of things that never get explained in detail and with intuition and with examples. So yeah,
Yeah.
amazing book. And speaking of of books, we also have Josh's book. Here's a page of it,
Yeah.
which is coming up soon, right, Josh? It's
Yeah.
a visual a StatQuest Illustrated Guide to Deep Learning. It's a sequel to StatQuest Illustrated Guide to Machine Learning. It's the
That's
part
right.
two, unlike Godfather. It's a part two that is
Exactly. I'm hoping I'll get
even
an
better
Oscar
than
this
the
time.
original.
Yeah. So this is going to come out early January 2025. So basically a month and a half from now. And the way I see it, I mean, it's a general introduction to neural networks. We start from the very most basic neural networks and we build all the way up to transformers, encoder only transformers, decoder only transformers. And we talk about those things. So it goes from the beginnings all the way to the state of the art. And it's the way I see it, and actually the way I end it is actually like, hey, you've made it this far. Now it's time to read Jay's book. Because so what's cool about it is, I mean, there's a lot of things cool about it. One thing I'm really proud of this book is obviously it's illustrated. You can see the picture here. It's got my classic style of drawing everything. Jay's book is also super illustrated, which is another reason why I feel like they're peas in a pod. So if you're visual learners, both books are going to be a great place for you. But also at the end of each chapter, I have a tutorial on how to implement that lesson or what we just learned, those concepts in PyTorch. And so by the end of the book, you're actually a pretty half decent PyTorch programmer. You start off with the most basic stuff and we just kind of build on it. And so that's a cool thing that wasn't really part of my last book, where I didn't have tutorials on actually how to do it yourself. And so this one comes with tutorials, and yeah, and it builds you up to the point where you're ready to start doing the practical applications that are in Jay's book. And so, because you've got all this background, I mean, there's lots of background in Jay's book as well, but for me, my favorite parts are when it actually shows you how this stuff can be used at your work, at home, all these places where you can actually apply these things. That's the magic there. So that's my book coming out in about a month and a half. So
very excited. And yes, I had the pleasure to take a look at it, and it's wonderful. And I actually have never seen a transformer fully worked out. Like I've always tried to do that, like try to go through the basics, but you actually go through a whole transformer with a tension mechanism with like a few numbers, and to me that's just the most amazing way, and very visual. So yeah, definitely recommend it if you want to learn LLMs. Definitely go to this book, and then you now have the two sources, which are these two wonderful books to learn LLM, and also two courses. Right, we have a course on deep learning AI from Jay on transformers, and a course also on deep learning AI from Josh on attention. So
that's right.
Whether you're a visual, a reading person, or a visual or a video person, you definitely have a lot of material to cover.
I think we can also plug grokking machine learning as an intro as well.
Luis's book. I just happen to have an image there. Just it's an oldie but a goodie.
So part of your 4 books to learn is definitely sort of this one, but also there's a 5th resource, which is LLM University, where Luis sort of broke down a lot of concepts around embeddings, and one of the most actual popular introductions to transformers is Luis's videos on transformers.
Definitely.
Thank you very much. Yeah, I enjoyed making those. I had a hard time understanding things like key query, so I had to make up my own understanding, and I had to look. When I look at matrices, I can the go-to place I go for matrices is linear transformations. So I had to wrap my head around attention using sort of visual things that move. So I have words moving on the universe. Let's say you have words here, and the example that I always use is if I say the word apple and you don't know if I'm talking about technology or fruits, but if I talk a lot about fruits, there's a galaxy here that kind of pulls apple here. Or if I'm talking about technology, it's kind of like gravitation. So I like to see it that way. So Yeah. Thanks for the for the plug. There's definitely a lot of
If I'm
material
to
there.
use that a little bit to kick off a question, like while I have the two of you here, it's like
Yes.
I really want to ask you about process and sort of
Process.
about your process in terms of breaking down a concept, making a video. So like how do you sort of approach these things? How do you approach, you want to make a video about topic X, like, or for example, how do you understand it? How do you think about it? How do you decide about the video? And then what's your approach in terms of what are the visuals? What is how do you sort of, you know, make the visual language, and how do you sort of plan out a lesson?
Yeah. You can go first. Yeah, I guess I take a while understanding stuff. I think 80 or 90% is understanding the stuff. And for that, I talk to a lot of people. I think I've had the two of you at some point against the wall asking questions. But yeah, I used to work with Jay and in person, so I would ask you a lot of stuff. I ask a lot. I try to do examples. I really think about it for months, sometimes years, at drawing things, just running in my head until I find the perfect example. But I always try to find the simplest possible example, like the tiniest, one, an alphabet of 4 words or an image of 4 pixels, until it finally clicks. And then yeah, the visuals, I start just kind of drawing stuff on Keynote, putting things together. And sometimes the making the images and the animations is part of my understanding. I'm like, oh, I move the word here, I move things around. But I would say 80% is wrapping my head around whatever the thing is and finding the perfect example. Yeah, the rest is, once I have that, I pretty much have the video. I don't know, you, Josh, what is your process?
My process is identical to Lewis's. I mean, it's all about finding for me, the math is, I can't, some people can just look at an equation and go, oh, that makes sense. But I actually have to run the numbers through it one at a time and see what's happening to them. And usually I try to do like intermediate graphs of what's happening, because they're just functions. Most of these things are just functions, right? So you can start off with an x-axis coordinate and you're just converting it into a y-axis coordinate or something like that. So I see what happens as I plug in different values, and how is the input, how does that relate to the output, and I'll draw graphs of those two things and generally get an intuition. And then, but a lot of it is like, how do you come up with that perfect example? Like Lewis was saying, you come up with this 4-pixel image or something like that. So the math is tractable and you can kind of do it by hand, or I can write a really small program to do it for me. So that's, so yeah, it's basically the same process of like, try to find the perfect example that I can use. What about you, Jay? What is your process?
So it really depends on the concept, and for some of them, yeah, definitely wrapping your head around it is absolutely the most difficult one. And for some, it's like reading a paper, reading a few other papers that explain it, the history behind it. Sometimes you have to look at the code to really understand a thing. Sometimes I need to run the code to actually play around with the thing to feel comfortable. So just the first part is just feeling enough comfort with the concept to be able to sort of speak about it. That usually takes some time, and then sketching the visuals. So even like when in writing the books, I would start with the visuals. So it's open up Keynote, go through, let's say, the various important concepts, and a lot of it's a complex picture. So this is the concept after it's all explained, and then maybe turning that into 3 previous slides where you show the concepts one by one, in terms of, first you need to know this, and then now that you know this, there's this other component here, and then that sort of builds up to that final picture of the concept, which, if you read papers, the figures that explain the concepts there tend to be that finally developed sort of picture where it contains 10 different concepts, for example, but introducing them one by one is a thing that sort of lends itself nicely to a blog post where it's to say, look at this, and then this other concept builds on top of it, and then this other one. And within this concept, always, the figures that I draw the first time are wrong, but they are essential for me to make the next version, which is a little bit more correct. That's a little bit of the thinking process, I would say.
I think you have a very flow diagram way of understanding things, because I've been in talks with Jay, and I'll normally like it starts drawing the flow diagram of what's happening,
Huh.
and there's like a beautiful one at the end of the talk. So I feel like everyone has their own understanding, right? Like I would be like scribbling a couple of numbers. I feel like Josh may be similar, right? Like I would just be like 1, 2, like I can't do X and Y. I just do.
Yeah, I can't do X and
Yeah.
Y. Yeah, that's for sure.
Yeah.
But yeah,
Cool.
I'm thinking about the illustrated transformer, Jay. That's sort of
Oh,
like
that's a yeah.
I don't. It's like a seismic event in the AI educational like landscape, right? When that came out, it changed everything. And one thing that was awesome about it was that I mean, because there's that image that they have in the attention is all you need, which is the whole transformer, and you just look at that and you're like, what the heck is this thing? Each part isn't that complicated, but when you put them all together, it's a kind of a nightmare. And you just walked through that thing one step at a time with all these illustrations. And I remember when I was learning about transformers, I was like, okay, this is where it comes from. It's like it was critical to my understanding. And also just one thing I thought was fantastic was also the fact that it's not just illustrated. It's you had like these matrices to show sort of how the shapes of the matrices would change over the multiplication. I can't tell you how many questions that looking at those matrices answered. Like I could look at it and goes, oh, okay, so that means this. By the shape of these matrices, I can deduce all these things that weren't initially clear when I read the manuscript, or were relatively vague. Because something is about neural networks is there's no real rules for how they should be made, and oftentimes there's different approaches to doing things. Like I can think of like 3 or 4 different ways of doing attention or calculating attention that sort of got thrown out along the way, but there's no reason why, like you see all these varieties. But when I saw how things related, I was like, oh, I see, I could answer all these questions. So it was a really amazing thing. I remember that was a big deal.
So like, a lot of it comes from just developing visual language, and a lot of it is from visual language sort of borrowed from the two of you, and sort of processes as well that you've sort of used. And a lot of it is empathy to the user, because that is exactly like my feeling coming across a difficult paper is like that intimidation and sort of being like feeling very uncomfortable with a specific concept, and
Yeah.
doubling down on that sort of empathy of not intimidating the user or the reader with so much information at the top. I'm a little bit intimidated by a block of code that is, let's say, not well, or lots of mathematical formulas that are, let's say, not explained, or things where you have to pay more, let's say, cognitive effort in terms of, okay, x equals k v, and then to understand that you need to translate what the k is and what the v is. So there's multiple steps of translation, where sort of building that visual language of what a vector is and what a matrix looks like on the screen sort of helps over time. And a lot of this is like in Andrew Ng's course when he was like for computer like intro to neural networks, and he was like, if this concept doesn't make sense yet, don't worry about it, just continue, like that, building up the confidence of the reader and the viewer by sort of building that empathy, I think is an important part of these explainers.
Yeah, you said that the magic word is empathy, and I think that I feel like when you feel I particularly always been a bad student. Like in school, I could never understand. I was distracted, and the traditional learning, like the formulas, do not work for me. The theory does not work for me. So I find that a difficulty makes it easier to feel what somebody feels when they don't understand something. And I feel like when you can relate to how somebody may be confused in a million ways, you can address that. And so I always try to think of myself as the student, like if somebody as distracted as me was listening to this, what would they want to hear? Yeah, I feel like there's a question on the live that's getting by Izumi. It says the question must be answered by all of you, please. How do you guys study new things? please give advice for newbie student and what you do now. So how do you learn like a completely new thing?
Well, I would say it really depends on the thing. A lot of what I tend to learn now is new methods that build on previous knowledge of neural network, of software engineering. Um, I do watch a lot of videos. If one of the two of you has made a video about it, or Letitia on uh, Mrs. Coffee Bean, or
Yeah, Sandra, who's also on the chat. I just saw her. She has good
uh,
videos.
yeah. So
Yeah,
a lot of the times, I would go into YouTube for if there's a good explainer of a paper, or a concept, because that sort of introduces the visuals. I would watch 3 or 4 of them if previously people have done that.
yeah.
Um,
I find that I try to learn by making it look like I'm not working. Kind of try to learn by trying to have fun. So one thing I've been learning lately is the piano, and I think I always put the same example. Um, but like I try to learn it by like just I don't know, just playing around, like playing some songs, not necessarily the theory. The theory comes later. And I feel like that's what I did with machine learning when I was learning it without really thinking. Like I went to some courses, but I actually just started playing with data, playing with fun things, like a little data set, plot it. So I feel like we have this sort of chip that tells us that you're supposed to learn in a class, that you're supposed to understand the theory fully. But I'm like, I think you can find the fun aspect of learning. Like I think if you can sorry, I'm having a bit of trouble. Are we still there, right? Yeah.
You're great.
So I try to have as much fun as I can. Like I try to look at examples and make it look like I'm not in a traditional learning process. Some people learn more traditionally, but I just look at a lot of videos. I read a lot of stuff. I ask language models a lot. Like now I go on ChatGPT and I go, I want to learn this, teach me this. I have this little example, help me understand in a simpler way. No, that was too complicated. Try again. And eventually starts grasping how you understand things. And I think it's been helpful for me. So yeah, just I think everybody has their own way of learning, and I think discovering your own way of learning is good, and it also helps you with teaching.
Yeah.
Yeah. How about you, Josh? How do you
Well,
learn?
so obviously the things you guys have both said are very true for me, but one thing I don't think is mentioned, but is possibly also true for you guys as well, is there's also there's a lot of fun involved in learning, but there's also for me a lot of fear involved in learning, in that or a
Yeah.
doubt, maybe fear isn't the right word, but doubt is definitely the right word. And that, I make videos that explain things, and sometimes I'm worried I'm not going to understand the things that I'm supposed to explain, and I'm just filled with doubt, and it's very scary, and kind of a stressful period where I look at this equation, I go, there's no way I could ever understand that thing. It's too complicated, too many Greek characters, um, too many parameters. There's, functions within functions within functions. I kind of freeze up the way I did when I was like taking a math test in school, and there was like calculus or something like that. And you integrate something that involved integration by parts. And whenever I had to do anything with integration by parts, I would just freeze up and go, there's no way I could ever do this. Um, and so there is a lot of fear and doubt that's involved. The and again, what we were saying earlier is I'll try to take the simplest example as I can possibly come up with and start running numbers through it. And when I start doing that, it kind of gives me confidence that, oh, maybe it's not that complicated when I just do it this way, one number at a time. It's just variables. If I just could think of it as like, well, what happens to the variable X? Like I can't wrap my brain around it, but I can wrap my brain around what happens to the number 2. Like 2 gets multiplied by something like 4, you right? and that's 8, right? I could do that, two times 4, no problem, right? And so, and that was a big change for me in neural networks. I remember when I was first learning neural networks, looking at a lot of fancy notation of matrix algebra, especially the matrix notation for back propagation, right? It's got this nabla form, and it's just it's like a nightmare. Like, it's so many symbols I didn't understand. But when I just put in one number and I multiplied it by a weight, and I could print out the weight was 3.27. So I could multiply the number 2 by 3.27. I can do that kind of stuff. And all of a sudden I was like, oh, I get it, and then the fear and the doubt goes away, because it's like, when you're a little kid and you think, there's a monster under your bed, and you can turn the light on. That's what using a small numbers are, that I can plug into my thing. That's my version of turning on the light and going, oh, there's no monster there. It's just a linear equation. It's just 2 times 4 plus 7 or something like that. I can do that kind of math, and then I feel I get, my confidence comes back, and I'm no longer freaking out.
Yeah, I love that, because many formulas are just a way to codify concepts, and when you codify it looks hard, right? Like anything, like if you take the happy birthday song and look at the notes, it looks hard if you don't know music, right? Like, but it's the song, right? Like, and I feel like the same thing happens with math. When I look at a formula, I get scared. And when you see what it is, it's just a way to condense a bunch of cool information, and if you can unwrap it, I feel like that's that's a good way to do it. Great. Well, we have a bunch of questions here, and I think a bunch of them are related to like learning. So let me read a couple that are similar. I think we can so I'm gonna read like 4, because they're all similar.
Okay.
Ashwin says, is there a linear algebra perspective to learn statistics? Concepts in statistics explained via concepts in linear algebra. Leo says, as a statistics fresh grad, what is the roadmap to learn ML and data science? Noral says, after learning statistics and machine learning, I feel like I'm stuck at this level. How can I upgrade my learning? And then Swamin Athbera says, how hard will the math in deep learning already? I've been struggling with machine learning. What prerequisite am I missing? Could there be an easy book that teaches all the math in short? So I think the overarching question here is, how do you basically learn the math in machine learning and the machine learning at the same time? How do linear algebra statistics combine? Like, if you have one, how do you get the other one, and vice versa? So does anyone want to add anything? I feel like one thing that we're talking that Andrew does is says, that don't worry if you haven't understood something, don't worry about the math. And I feel like that works for me, right? Like, if you're learning machine learning and some mathing you don't know, then go look it up, because now you have the application with it, right? So many people say, go learn a bunch of math, go learn a bunch of linear algebra, a bunch of statistics, a bunch of calculus, and then come back and do machine learning. But I'm like, to me, that's weird. It's like if a kid is learning to play soccer, and what's the first thing you do? You tell them to kick a ball, right? You don't say, read this book on soccer strategy and techniques and rules, and then come back. But if the kid is kicking the ball, at some point, it gets to start learning some techniques and some rules, and then you start reading chapter 1 of the book while you still play. So I feel like you shouldn't be discouraged if some math looks if you don't know some math. Like, go play with the machine learning, and then when math concepts come in, they will be clear.
I would echo that. So for me, playing with the code that sort of does the thing has been helpful. So the first time neural networks really clicked for me is an example that Andrew Trask, a blog post where it's training a neural network in 11 lines of Python. So, having a sense of the concept, a vague sense by looking at papers and some math, but then playing around with it in code and being able to change things and see how it behaves. Like, usually that interaction tends to be the final thing where everything clicks for me. But to also get there, seeing explanations that are high level just give you the intuition. So there's no way by reading the paper of, say, I don't know, PCA or something, or the Wikipedia article, which is an impossible thing to sort of learn from usually. It
Yeah.
describes a thing
Yeah.
very succinctly, I guess, but it's not for a learner. But then that's where sort of, StatQuest and sort of explaining these concepts one by one, and just the intuition. Like, I must have the intuition first before having a crack even at the math.
Yeah. It's a good question here by Sandra. How do you find inspiration? How do you decide what to focus on when there's so many concepts out there to explore? So how do you decide where to go?
So I have an advantage that most people don't have, which is lots of people commenting and asking me to explain things. And I basically, in the back of my head, I have a histogram of what people are asking about, and I can kind of get a sense of what is hot just because everybody's asking about it all the time. And so then I'll be like, well, what is that thing that they're asking about? The curiosity. I can't resist it at that point because it gets the best of me. And so I that's how I kind of figure out what I want to do next. Sometimes I have got like master plans of like courses I want to do and topics I really want to cover, but usually it's just I get so much feedback from people asking me that I kind of have an unfair advantage, I feel like, in terms of inspiration, because I've got people constantly asking me these things, and it's all very cool. I mean, to be honest, it's even the stuff that isn't because people ask me about everything. They might be in some very niche field that has some very niche method, and they'll ask me about it. And I'll be honest, it's all interesting. That because it's the same process. It's a function that transforms an x-axis coordinate into some sort of y-axis coordinate, and they're all the way they do it. The concepts or the way they do it is all pretty fascinating, and so it's nice to know that like most because I wouldn't be able to choose otherwise, right? It would just be this flat landscape of awesomeness. But because I've got this histogram, I can kind of get a sense that most people are going to be interested in this topic. So maybe I should focus on that one first as a way of prioritizing things.
Mm-hmm. Flat landscape of awesomeness. I'm going to use that one. Yeah, I have a similar thing. Like I'm always trying to understand like 20 things, and some of them never click. And some of them start clicking, and sometimes something that I've had in my head for a long time is like, oh, click, and I'm like, oh, okay, I'm gonna focus on that. Obviously, trends are important. Like if you see everybody worrying about a certain thing, everybody talk about something. If you have the channels you follow, like the people you follow, and then that helps a lot. But yeah, I think I'd like to use kind of joy as my compass. Like if I find something fun, I try to learn it. Yeah, I don't know.
Yeah, that histogram for me a lot of the times is, for example, social media, the people that I follow, what excites them, that informs a little bit of which clicks into curiosity. So what triggers your curiosity? What are you interested in? Because that is powerful. That will be a force sort of that pulls you in. It's a big part of what Luis refers to as joy or fun. It's answering a question because you have a question mark. It's very hard to pursue it if you don't have the question mark or the interest to actually learn it. So following that curiosity that develops a little bit in part in terms of what is interesting to people around me, that whose opinions or whose focus is close to mine.
Yep. And also not just in the topic, but also how to approach it, right? There's a question here by Anna. Says, should we dig deeper into LLM AI, or should we focus more on the application side and build products? And what I would say is I'm lucky we have both kinds of people, right? Like some people are more like, I need a product application. I'm glad if everyone's like me would have all this visuals and know stuff done. So I'm glad that and I think to Anna, and I would say the answer is like whatever you enjoy more and whatever looks easier. I, for example, can write code, but not for a living. Like I don't really get into it that much for production code, but other people love it, right? And they don't not so concerned on how this matrix does this with that weight, but they want to put it in production and get a nice product. So I think the answer is whichever one you you enjoy more, and for everybody. Like the AI has a business side, AI has a production, technical side, it has a sort of intellectual side of understanding, a research side, and as I say, I'm glad there's people in all of those. Just pick whichever you enjoy more, whichever one just kind of feels easier. I just kind of go for whatever I gravitate to. Yeah. Anything you guys want to add?
Yeah.
Let's see. Here's one question by Kevin. Says, to effectively learn machine learning, what algorithms should I focus on? Any thoughts?
I always have the same response to this,
Uh-huh.
which
Let me
is
see.
start with the basics, start with the classics. They're still cool.
Yeah.
I say this every time, like linear regression has been around for forever. It's
Yeah.
still useful. It's still awesome. It's still, just because we've got fancier tools doesn't mean that the basics are no longer useful. And so I always just say start from the beginning and start with the basics and the fundamentals and build up from there, because those things are never going to get old. And to be honest, transformers are cool, but I also have a feeling that they may not be the big deal for the rest of our lives, right? So don't throw all of your, everything into that one basket, right?
Yeah.
Yeah. And yeah, some things, as just some things are evergreen, right?
Yeah.
Like the basics are never gonna go old, like
Yeah.
because we just build up on them, right?
Yeah.
A transformer is a big neural network. So if
Yeah.
you learn neural networks 10 years ago, you didn't waste your time.
Yeah.
If you learn them now, you're not wasting your time. And some things go out of fashion. There are algorithms that just no longer are good, but the concepts are important.
Yeah.
So I feel like
Yeah.
the ones that we don't use anymore, that's because they've evolved and stuff like that. So I think yeah, definitely start with the
Yeah.
linear regression, logistic regression, anything related to trees,
Yeah.
anything probabilistic, like base things like that, and neural networks. Neural networks. I think for a while we're still going to be using neural networks. Like maybe one day we'll get something different, but I
Yeah.
think they're like everything that comes out now. I almost look at it knowing that it's a neural network with some boosters.
Yeah.
Uh,
One
yeah.
thing I want to add to what I just said, can we get back to Jay's new book? One thing I loved about that book was,
You mean this one?
yeah, exactly, this book that everyone should buy. One thing I loved about it was, we're using these, transformers are big and relatively expensive to use. And in this book, what they do is basically show how to combine transformers, which are big and expensive to use, with traditional machine learning methods like logistic regression, which are
Mhm.
cheap and small and cheap to use. And so they were using like a class, using an encoder only transformer to create embeddings for classification, and we could then use those embeddings as variables in a logistic regression to do really like cheap and easy classification after that, right? So I thought that was a really clever use of just sort of time and money. We don't actually need this huge nuclear warhead to solve all the problems all the time, right? We can sometimes smaller, simpler things that are fast and cheap can get the job done faster and cheaper, but it still is just as good. And so that's another reason why I think the fundamentals are crucial. Is they're not even with the advent of large language models, they're not going away. They're still useful. They still have a place in sort of a modern data analysis pipeline.
Absolutely.
And that matters a lot for application, even if you're, let's say, building things in industry. So that's one of the hidden agendas of the book, is to actually, put forth things that are less flashy, but are more the best tool for this job. Yes, you can throw so many different problems at a trillion parameter model, but it will do it expensively, it will do it slowly. And you have smaller models that sort of are able to do these things more reliably, more robustly, little worry about hallucinations, which is also, when you're building a product and selling it, it will make your product faster and easier and sort of better latency, and more successful. And so, yeah, a lot of it breaks down into these ideas. So logistic regression, neural networks, backpropagation, but also things like PCA and k-means clustering, which all applies to working with language models. But they're all sort of very important tools to think about this, multidimensional world of representations, of how words are represented, how documents are represented, how images can be represented, like numerically using these models, and they all build up from
Yeah.
these fundamental concepts.
Yeah, I think embeddings is very important, right? Like if you have the concept of an embedding, that's not going to go old, because any information that you have, whether it's video or images or text, like you put it through an embedding, it becomes numbers,
Yeah.
So that kind of stuff. And another holistic concept that you mentioned, sort of, it's like ensemble methods, right? Like that is used all the time in things like a mixture of expert or something, like just the fact that, or even inside a neural network, the fact that you're going to build a problem and you don't have one friend, you have 10, and this one's good at this one's good at that, this one's good at that, and you can just sort of split it and then combine it. That notion will never get old, and
Yep.
we keep using them. Yeah.
Yep.
So now that we're talking about Jay's book, there's a good question that I actually want to ask Jay. Is how does the size of the vocabulary affect the LLMs? Do they suffer from OOV, which I think is out of vocabulary, or does the type of tokenization compensate for that?
So it depends on the method of tokenization. So high level, for the model to process text, it needs to be broken down into chunks. These are words or parts of words. And in, let's say, earlier models from 5 or 6 years ago, you defined them as, let's say, even like things like word to vec. You have a vocabulary of, for example, 300,000 words. These are the words that the model knows. If any new word comes, you have no way to represent it. But then more recent methods for tokenizations have fallback tokens that can be used to represent everything. So each, for example, letter is a token on itself. And so if this new word cannot be represented by its own token, it can be represented by the tokens representing the letters, for example. Things get a little bit more complex if you want to represent multiple languages that are not, let's say, all spelled in English letters. And so the fallback here is to look at Unicode and UTF-8 and how that is broken down, and then what bytes, for example, can be used to represent everything from emoji to all of the different languages. And so more and more, these byte pair encodings tokenization is initialized by saying, okay, this is an initial flat, let's say, set of characters and bytes that can be used to represent everything that we can, or most things we can represent in Unicode. But then on top of this, let's hear, the 50,000 most used, let's say, parts of tokens. And this is a training process. You define, let's say, a tokenizer. Let's say you want to give it 100,000 or 200,000. A lot of the recent models have vocabularies of this size, and then that you train on a data set. This is apart from training the language model itself. It's a tokenization training to find the best tokens that can compress your data set. And so if your data set has code, for example, you need specific tokens that represent things in code. So for example, you need one space to have a token, you need two spaces to have a specific token, up until sets of 70 spaces to have a specific token, because when you're representing code, indentation is very, very important. And so spaces and tabs, that has a direct effect on the model's ability to generate code properly and sort of keep track of indentation, for example. We go into sort of tokenization and compare everything from BERT to GPT-4 and Galactica and some of the more recent models, and show by example how they differ and how some information can be lost if the tokenization is not sensitive to that kind of information.
So here's a question. Let's say I have the word unhappiness. A small vocabulary will split it into like on, happy, and ness, right? A big one may have the word unhappiness in its token, right?
Yeah.
Which one of the two would be better for recognizing another word that's not there? Like if I have unjoyfulness, which somebody made up, but in theory, like we would love it for it to understand, even if it's not there, right? So
Yeah.
what is better?
It's really a trade-off, because if you have unhappiness in one in the token, do you also have unhappiness in all caps as one word in the tokenizer?
Okay.
Do you have unhappiness when it's only the U is capitalized? Do you have that as its own token? And if you have
Oh.
that, you sort of your tokenizer blows up in size. But then on the other hand, if you're representing most things as smaller tokens, uh, you might run into the limitations of context size. So if your sentence is, let's say, 100 words, and each word is 15 tokens or characters, if you break it down, like your word, you can represent less and less text inside that context of the model. And also you give the model more of the responsibility to represent these things, and sort of model. So it's really a bit of a trade-off between the two.
So if you have too granular, that's bad.
Yeah.
If you have too big chunks, that's bad. And there's like a Goldilocks
Yeah.
period in the middle. I'm guessing that depends on the data set, right? Like if you have a
Exactly.
data set with a lot of, like the SAT words data set is different than a random Reddit thread data set or something.
100%.
Okay, great, great, great. Actually, I just realized if I click on things, they appear, right? There's a question
Oh,
from Nikhil
cool.
says, what do you think is going to be the path for AGI? Attention in itself is not for sure, right? So AGI, what are your thoughts on AGI?
Josh, I'll let you.
Yeah, I mean, I've been long advocating for more biologically based models. So the history of neural networks is sort of one of ups and downs, and these sort of like neural networks winters and things like that. But throughout the history of neural networks, they've always been trying to model some physical property of intelligence. Like the very first neural network ever, which came out in the 1950s, was trying to, it was called a perceptron, and they were trying to model perception, specifically how to recognize characters with photoreceptors, and how to process those and classify them. And then, they had a it wasn't a great design, let's be honest, but it was a start. But nothing happened for the next, I don't know, 20 years. And then along came, convolutional neural networks in the 80s. And it was another big breakthrough. And they came up, but again, each component of that convolutional neural network, they could map that to a certain biological property of how an eye functions, how the brain functions. Um, and that's sort of been a tradition in neural networks, for better or for worse, because there's been some limitations. For example, for a long time we used the sigmoid activation function, and a lot of people still teach basic neural networks as like, you have this activation function as the sigmoid activation function, and that was based on sort of how neurons fire, and how they've got like sort of a maximum potential and a minimum potential, and sort of a range of values between those two, and it kind of saturates the maximum and things like that. That was all, and it was great, but it also it limited how deep neural networks could be made, because that sigmoid is kind of hard to train, because when you get off to the edges, you're the tangent line, which defines how quickly you can learn, basically goes to zero. And so it becomes very difficult to learn, because the rate of learning it approaches zero. And so they got rid of it, and they replaced it with something called the ReLU activation function, which is like less biologically inspired and more just like, let's get this done. And I feel like a lot of the transformer architecture that we have now is, when you read that manuscript, at no point do they go, and this part corresponds to this part of the brain, and this part corresponds to this brain, like they used to back in the day. They're just like, these are the parts, and this is how it works, and it's awesome. And I think for most people, they were like, that's great. What we want is something that works, not necessarily something that's a great model of how the brain, the human brain or a mouse brain works. But I do think that there's still a lot to be said about inspiration for how biological learning takes place. It's not just all neurons. There's a lot of chemistry going on as well, in terms of like gradients of molecules, and how we've got this thing where there's like these dopamine receptors that affect windows during which we can make associations from things. Say like someone says the word ball and I see a ball. When someone says ball, I hear the word ball, and all of a sudden, but but I don't know what a ball is. Then nothing really happens. But if I'm holding a ball and I've got receptors that are firing in response to me holding this ball, and then someone says that's a ball, there's a window of opportunity where I can associate those things, and then it stops, right? I can only make those associations at certain times, and I just wonder if is there a way to model these sort of like dopamine responses to learning? Can we incorporate that into the model? I don't know. I just wonder about these things as like the next step. I could be totally wrong and way off, but that's my soapbox of
Love
that I
it.
stand on when I talk about these
Yeah,
things.
I love the scientific approach.
Yeah.
Yeah.
Full disclosure, I used to be a geneticist. And so I've got a background in biology that spans many, many years and just a love of it. So that's my I've got biology goggles on when I see the world. I'm like,
Love
sure,
it.
surely that will inform us.
I think that's the great thing of AI, that people come from different backgrounds, and you see it from the biology side,
Yeah.
and I see it from different sides, and we get to see a much more high dimensional
Yeah.
object. Yeah. When it comes to AGI, I'm pretty torn, right? Because I feel like the more machines can do, the more we have to step up and find higher levels, right? Like when machines can start doing our mechanical things, we decided we have to start being thinking more. And now that machines can do a lot of our thinking, like I don't see much limit in terms of rationality. Now I'm a mathematician, I see everything through the math angle, and I feel like, I don't know, I feel like they can do better math every time, and better science, and it's gonna be like trying to run faster than a car. It's gonna be trying to do better thinking, rational thinking than a computer. So I tend to think a lot of like, are we done? Like, do we have anything left? And I feel like we just have to find other aspects of intelligence that like, I think an AGI can be as, I'm gonna say this and I may be wrong, but I predict that an AGI can be as intelligent as a human being when it comes to rational intelligence. And I feel like where we tell ourselves apart is in things that are not rational intelligence. So things like emotional intelligence, things like empathy, things like even like our intuition, when you have a hunch or things like that. Those things we have, the computers don't have, and I think we need to develop them more, because the computers are going to do most of our thinking. I don't know.
So part of this general discussion about AGI, like there are a couple of things that I find a little off-putting in the discourse. One is, it's not always very well defined, and different people have different definitions of what the AGI is. And second, there's a little bit too much maybe hype around it, and maybe overselling that comes around with the discussion. So like when I think about it, I think about it in two different distinct, let's say, universes. One is in the current generation of technologies and sort of where we have line of sight, which is, we still have a lot in terms of improving the models for things like reasoning. They're still, so much smarter than humans in some aspects, but so much, let's say, less smart in other aspects. So they're like a different kind of intelligence. And in this first, let's say, aspect, it forces you to, look at biological and other types of intelligence. So human intelligence, we have a bias to think about human intelligence. That's why AGI we think is a big thing. But there are other more sophisticated, some of them biological for specific tasks, kinds of intelligence. And so I'm really interested in how can we make the current generation of models more reliable, more useful to actually solve real world problems. But then also I'm interested in throwing the technology that we have at understanding, for example, the languages of other species. So there's a lot of research on decoding dolphin languages and whale vocalizations and elephant. Um, I find that quite fascinating. To understand other intelligences that are out there. So this is all in terms of thinking about the current state of intelligence, and then another way of looking at it, another set of goggles, is science fiction, and to see, just regardless of what type of system that gets us to something like that, what can the world be? And so science fiction sort of, there are a lot of extremely competent and smart authors that think about the various that have thought about various utopias and dystopias for once AI is here, how should it sort of interact with humanity. The Culture series of novels is one of the best to sort of think through that. But I do find it useful to think about it in two disjoint ways of thinking.
Yeah, great. I think actually, we're close to time, but that's a good segue to the next question. But before that, I'm going to show this comment, which is fun. I think stream is like the Avengers of ML educators. Thank you, Andy. This is a great segue to, I think, maybe close to our last questions. Walker says, what will be disrupting topic technology in future, like transformers? So Jay, you're thinking about like what coming up in tools, etc. You're mentioning. So what do you think are the next big things?
For me, the most fascinating thing is code generation, language models. So this is a little bit of the agentic behaviors of these models that can generate code, execute that code, and sort of reason through that and interact with APIs. There's a lot of work in companies and startups sort of innovating in this space, and it's still in its beginnings. But once an agent sort of solves a problem at a high, once that happy path happens, it's fascinating, and you see it, and it feels that this will definitely change the future of computing, and that's one of the areas that is absolutely interesting to me at the moment.
Nice.
Can I add to what Jay said? Maybe giving some cool examples of that style. Like, imagine, you say, I want to go on a trip to Mexico or something like that. And I mean, there may be a program already written that could take care of that kind of query, but imagine if there isn't, but you've got an agent that can then on the fly write the program that solves that problem and gets me the ticket. That kind of thing, where we don't have to anticipate all the cases that we might need a program. We can write them on the fly as needed. I think that's going to be kind of and execute them and everything. And that's going to be transformative when the code doesn't have to be written in advance of whatever we need to do. It can be written on the fly. I think that's going to be a big change.
Yeah, I agree with that. When I look at technology, how it evolves, I think they tend to mimic each other. I see, like, for example, how the internet started, and before it was just text. Well, like, information goes in, you get information and give information, and that's all. And one thing happened, which is what you two mentioned, which is the tools, right? Like at the internet, you started being able to make bank transactions on the internet and buy tickets, and like it became not just an information thing, but it became a bunch of tools, and people will make the tools, right? So I feel like with transformers, like, people are gonna start making the tools, and they're gonna become like a Swiss Army knife of things. And another one is multimodality, right? Like with the internet, first it was a lot of text and maybe an image. Now it's like all just video, chat, these type of things. So I think a next step, which is already happening, is to have, the inputs and outputs could be anything, right? Could be a video and then sound comes out, etc. So I see those two things. Yeah. So cool. We are close to ending. Should we take let's take one more question by Sandra. It says, Sandra was working at Cohere, right? Actually, hi. Do you feel like you go deeper and broader with time, or do you feel like you hit walls in certain places?
Oh, I know I hit walls in certain places.
I hit walls all the time.
Yeah, exactly.
All the time. Yeah.
Yeah.
Actually, I feel like I get broader at some point where I was just trying to learn one thing, and now I feel like I try to learn a bunch of different ones. So I may be broader. I feel like people do the opposite in general. Like, you start wide and then narrow down into something, but it never worked out for me. Like, to me, it was mostly getting more broader, and maybe you learn things less deeply, but the fact that you're broad means you can find connections.
I think that's because you're a mathematician and it's all math, right? You can learn about one thing and it turns out to be true about everything, right? It's
Maybe,
just
yeah.
inherent with the mathematics and the generalization of it.
Yeah.
For me, it's like I go deep for a while, and to be honest, until I kind of get bored, and then I kind of find something new. So because there's, I don't know, there's just, like I was saying, that flat landscape of awesomeness. That's maybe a genuine weakness that I have, where I look out at all these things, and to be honest, they're all interesting to me. And so I just want to be broad all over the place, but you can't really do that and succeed, I don't think, right? There's a lot of talk about hiring people, like T-shaped people, right? People that have a little bit of knowledge of all kinds of stuff, and then tons of knowledge of one little niche thing. And I think there's a lot to be said about that, where you've got your expertise, but you also have like somewhat of a big, a vague sense of what the big picture is. But for me, it's sort of like I go deep, and then I come back up and I find something else to go deep into. And you can see that in how I create videos, where I'll create a series, like an exhaustive series on logistic regression. I went so deep into that, and I thought I'd never come out, but eventually I was just like, okay, I can't do this anymore. Let's do something else, so I won't go crazy.
True. And things like the momentum of the channel and what people relate to, or what kind of audience sort of also, for example, nudges you in one direction or another, I would say.
Yeah. Well, I feel terrible, but there's a question that I want for me.
Okay.
And then we finish. Because we started a little late. Because I want to ask you guys for this one.
Yeah.
What do the query key and value vectors in the transformers say to you? So, like, question by Sanjeev, could you explain the significance of query key and value? I think we all have a different answer, which is great.
Yeah.
How do you guys see the query key and value matrices?
Do you want to, since this is for you, do you want to start with it?
Who, me?
Yeah, Lewis. Yeah.
Well, I don't understand key query value matrix. I've seen various explanations for it, and the only thing I could do was multiply the key and query value matrices and use that as a linear transformation. So I actually think of them together. So I think, for example, let's say you're embedding. Let's say you have a good embedding. Your embedding is fantastic, but you could have an awful embedding for some topics. Maybe your fruits and here are your cars are here and they're too close and they should be farther. Well, you can apply linear transformations to widen your embedding space and fix this problem, right? And to me, the key and query and value matrices are ways in which you transform the embedding space to work for you. And you do random ones and then start training like a neural network. And then eventually you end up with, let's say, 12 or 20 really good embeddings for certain things. And then you have like a router that just says, you know what, when you're talking about pizza, you want embeddings 1, 4, and 6. More than 13 is really bad one. But when you're talking about tractors, 13 is really good and 20, but the other is not so good. So it's kind of like the concept of getting your getting your friends to help you in something. The ensemble methods or the mixture of experts works like that. So that's how I see them. I'm still trying to understand key queries and values by their name, by like what are you searching in what database. But if I see them as linear transformations, I feel like that's what helps me. I don't know what about you guys?
I would say sort of my intuition is, and there is a paper by this title that feed-forward neural layers are key value memories. So you can think of, I think, keys and values as one thing, and then queries as another thing. So if you think of, let's say, attention as a database, for example, and the query is what's, let's say, the current thing that you're looking for. It's your search query, for example, and then the other one is the other vector is what information to bring. I have a visual of folders and a post-it note in the illustrated GPT-2 visual, which is how I think about it. Let me see if I can post that in the chat.
Please put the link. Yeah. By the way, Illustrated Transformer got revamped, so people who read it should read it again. Right?
Done. Will do.
Cool. What about you, Josh? How do you see keys and queries and values?
Yeah, so I think it's right. I think I agree with it. I mean, I agree with both what you guys are saying, but I think what Jay was saying kind of resonates with me in terms of like the query and then something else, key and value, you can kind of lump them together. The idea being what we're generally trying to do is measure some sort of similarity between what we have and what we know. And I feel that's the relationship that I think is interesting is quantifying that relationship. And some of what we know is going to be more pertinent to what we have, and then others, just like you were saying, right? These embeddings are more helpful for pizza, and these other embeddings are more helpful for tractor. And it's just a way of quantifying those similarities and allowing the network to focus on those similarities. And that, for me, the keys and the values things, why they keep that separate for me is I just think of it in terms of it's also advantageous to add more weights to your network because it gives you just more flexibility to a certain degree. And so I think that's why they've got those separated out. I mean, there's other reasons, but that one of the benefits of having that is you get the extra weights.
Yeah.
So
cool. I love it. I love that we had that different intuitions. Well, I think we're over time. We started a little late, but we're at the lower. But we've had such a great time. A lot of questions that are there that are really good, and we won't get to. But please, let's do this again, guys. I'm so happy.
Let's do it again. Hooray,
so
Jay! We have to come back.
Much from you guys. Thank you so much for being here and for your insightful answers. So to the crowd, don't forget to get this book, Hands-on Large Language Models. And this one, StatQuest Illustrated Guide to Deep Learning, which is the sequel to this one. StatQuest Illustrated Guide to Machine Learning. And thank you so much, guys. I love talking to you. It's such a great time. And let's
and don't forget Grokking Machine Learning by Louis Serrano.
That one too. Definitely.
There it is.
All right. We should do this again. I'll announce something on LinkedIn for the future. Thank you, everybody, for coming. Thank you for great questions.
Thank you so much. Thank you for having me. Good to see everybody.
Bye.
Bye.